welcome and thank you for coming. We're going to get started now. So thank you for coming tonight to the third talk in our STEM Education Colloquium series, which is a part of the Barnard Teacher Scholars Program. Tonight I have the honor of introducing one of my esteemed colleagues from across the street, Dr. Lam Hui, who I recently met when he approached me about wanting to start an enrichment program for preschool and elementary age kids in math and science, which sounds like a really exciting project. But as I got to talk to him, I found out that not only is that an exciting project, but what he's working on here is also very exciting. So Dr. Hui got his undergraduate degree from Berkeley and PhD from MIT, both in physics. He worked at the Fermi National Accelerator Laboratory, the University of Chicago, and the Institute for Advanced Study before moving to Columbia University, where he's currently a professor of physics with a research focus in theoretical cosmology. So tonight, our talk is going to be focused on physics. And for those of you who are in the STEM Colloquium course, I'm going to ask you to really think about where the sciences, as they take place at the university level, fit into our conversation of K-12 education and what it means in terms of STEM education, both in preparing scientists for the future and other people who are going to be working in STEM fields, and also thinking about how science teachers in particular need to stay current and invigorated to be scientists and not just get caught in the mundane day-to-day teaching. So as we move forward, I'm going to turn it over to Dr. Hui, and welcome.
Thank you. Thank you for, thanks. Thank you for the invitation, Lisa. Thank you for coming. Lisa asked me to talk, I wasn't quite sure exactly what I should talk about because I understand the focus here is really on education, which, by the way, is something I care about a lot, both at the university level and, as Lisa mentioned, we have, at least we have an idea about an education project that has to do with actually small children. What I will do in the next half hour or so is I want to tell you a little bit about actually my research, and I frame it using music, and I use a phrase kind of from actually past history, music of the spheres. A long time ago, when people started actually exploring outer space, looking at the planetary motion, for example, around the sun, it was understood that somehow the orbits of planets around the sun follow certain patterns that resemble harmonies in music. And it was believed there is some form of celestial music out there. You might not be able to hear it, but you can recognize it when you see it. And that theme is actually fairly appropriate for what we actually understand now about the larger universe, which is really what I study. My field is cosmology, in particular, basically studying questions that have to do with the universe as a whole, as opposed to just individual parts of the universe, especially about the history of the universe, how nowadays we know the universe actually had a beginning about 13.7 billion years ago. And I will tell you a little bit of a story actually about that history. So first of all, I want to show you, it was a question that I was asked at some point. We have all heard that the Big Bang happened, right? The universe started with a bang, with an explosion. You might wonder, well, what did it sound like? If you were there, what did it sound like? So I'm going to play what a reconstruction. It would not make a whole lot of sense to you when I play, and it would not be a little bit, as you will see, a little bit anticlimactic. But I'll explain to you the science behind that music, and hopefully it will make more sense the second time you listen to it. Here's the first time. That's it. This is isn't it a bit anticlimactic? This is made by an astronomer, by the way. I gave him credit here. This is supposedly, at least this astronomers, to the question, what did the Big Bang sound like? And it didn't sound like much. It sounded like some kind of noise, doesn't it? It sounds like radio static. And I want to kind of unpack it for you a little bit, and then at the end I'll play it again for you, and hopefully it will have more meaning towards the end. I want to organize what I want to say in the form of a number of questions, and these are all questions that are very natural. It occurred to a lot of people whenever the subject of kind of the beginning of the universe or the structure of the universe comes about. So here you go, the first question. How big is the universe? Natural question. How big is it? So I want to give you a sense of how big it is, okay? And I'm going to step through a number of things in the universe just to give you a sense of scale. So here is the image of a galaxy, which is probably very much like our own, the Milky Way. Of course, this could not possibly be our own galaxy, because the only way to take a picture like this for our own galaxy is for us to fly a rocket all the way up above our galaxy and take a picture snapshot from way above. Our galaxy is in the form of, it's kind of, think of our galaxy as like a piece of pizza. It's a disk. And we are actually somewhere on the outskirts of the pizza, not quite in the middle, somewhere on the outskirts. It's a plane. And this picture is a snapshot when you look at it from outside the plane. Yeah, you're looking at the pizza from the top. And our galaxy does seem to, as far as we know, have these spiral patterns. These spiral patterns are just basically a collection of stars, many stars. There are billions of stars. And our very own sun would be one of these stars somewhat on the outskirts here. And I want to give you a sense of scale. And the size of a typical galaxy like our own is this many centimeter. I hope it makes some sense to you. When I say 10 to the 23, I mean 1 followed by 23 zeros. Sounds like a big number. Let me give you a sense of how big this number is. Suppose I tell you that this galaxy have billions of stars, and I want to I blindfold myself and randomly point, and I ask myself, I want to point right at the sun, randomly point, and find where the sun is. That will be analogous to what? To say, let's say you randomly point on, let's say, on the surface of the Earth, and you randomly point and you can pinpoint a piece of hair. Can you imagine that? So our sun is that small compared to just one galaxy, and this is 1 followed by 23 zeros centimeters. So this is already a big object, right? Very big compared to certainly our daily life scale, certainly much bigger than the sun. The sun is already 100 times the size of the Earth. We think the sun is big, but this is certainly a lot bigger. Okay, so that's a galaxy. Now, for someone like me, what I study is actually not so much individual galaxies. We go bigger. So I'm going to show you something that is 10 times bigger. And this is an image taken by the Hubble Space Telescope. You might have heard of that. It's a telescope in space. And if you point that telescope to just any random part on the sky, really just any random direction, and take a very deep image, meaning you just expose it for a long time, you will see something like this. There's nothing unusual about this field. And if you take a deep enough image, you will see the universe is full of galaxies. You see these basically extended objects. These are all galaxies. Each of these extended objects is a galaxy like the one I showed you before. Yeah? And this image, the size of this image, roughly speaking, is 10 times bigger. So that's why it's 1 followed by 24 zeros instead of 23. So this is 10 times bigger. And the universe is, once again, filled with billions of galaxies, just like a galaxy is filled with billions of stars. And this is fairly typical. If we look sufficiently far away, we'll see lots of galaxies. So that is 10 times bigger than the previous one. So let me go another 10 times bigger. Yes? This requires a little bit more explanation. Each of the dots here is one galaxy. Okay, so each of the dots is a galaxy like our own, the one that I showed you earlier. And what this represents is what we call a galaxy survey. This galaxy survey is pretty old. It was done at the Center for Astrophysics at Harvard. This galaxy survey is old, is about more than 20 years old now. What this map of the kind of the local universe illustrate is something like this. Imagine you are in the middle and you're looking out, and imagine you point your telescope on the sky. As the Earth rotates, your telescope would automatically scan the sky like this, yeah? As it scans the sky, imagine you are taking a kind of a slice of a pizza on the sky, and you just ask yourselves, where is each galaxy on that particular slice? And you just plot it on this diagram, where if the galaxy is further away from you, then it goes further out this way. This is the angle direction. This is the direction away from you, yeah? And we have two slices like this, one in the north and one in the south in this kind of diagram, okay? What you notice is that there are very interesting structure out there. If you look at very large scales, once again, this is 1 followed by 25 zeros, so it's 100 times bigger than the first slide I showed you. The galaxy distribution is not random. It has some structure to it. You see these great walls, we call great walls. You see regions where we call great voids, regions where they're fairly empty, no galaxies. Interesting structure out there. There is, I won't have time to go into it, but if you pay attention, there's something mildly disturbing about this picture. I wonder if caught the eye of any of you. Do you see anything disturbing in this picture? Yeah.
It's the long dot on the side.
This one for is just an artifact. So the data, in fact, I should have mentioned that the data was not collected in this direction for a simple reason. Do you know why? It has to do with actually our galaxy, right? Our galaxy, remember, is a slice of pizza like this. So all the stars in our galaxies are aligned in a plane like this. We live inside this plane. So as we look out in this direction, this is north, this is south, this is what we see. But if we look actually in this direction, we'll just see all the stars in our own galaxy. And they are so bright, it's very hard for us to see anything further away. So that's why we just block them out. We don't actually do galaxy survey in what we call the galactic plane. So this is probably just an artifact. The thing that is mildly disturbing, it was interesting the way astronomers choose to describe it. If you look at these alignment of galaxies, you see they tend to, at least some of them tends to form these line segments. You see them? Mm-hmm. And strangely, they are all pointing at us. This is where we are. So astronomers who first saw this called this the fingers of God. If I have time at the end, I'll explain to you where they come from, but it's mildly disturbing. Okay, let me go another factor of 10 bigger. This is like almost the state of the art. In fact, the state of the art is even a little bit better than this. So this is another factor of 10 bigger. On the left is shown basically the same kind of map that I showed you in the last slide, except this is looking a lot further out. Each of the dot, once again, is a galaxy, and is even hard to see now individual dots because there's so many of them. Ignore the coloring. The coloring is just supposed to show you red is closer by, blue is further away. So just ignore that. But this is what the universe looks like if you look really far out. And this is what it looked like actually if you just take a picture. Think of it as just a picture that, you point your telescope, it's basically a camera. You take a very deep exposure, and like the Hubble Space Telescope image, you see lots of galaxies. And if you are looking, take a very deep exposure, you are able to pick up very faint objects, which of course means they are very far away. That's why they are so faint. And therefore, as our technology gets better and better, our abilities to see further away objects gets better and better. And so that's why over time we are able to map this out further and further. The galaxy survey that I showed you in the last slide is about 1/10 of this size. So it's basically just this little chunk around in the middle, right? So we fill this out now, factor of 10. Yeah, Maria.
So my question is, the north seems to be a little bit denser than the south. I mean, is that just the tool that's measuring in the north versus the south?
I think so. I think.
It's the same thing in the other picture, actually. It seemed like there were more stars in the north than in the
Let's see.
south.
That's right. It's true. Locally, it has been pointed out there's a kind of a lack of stars, or at least there are bigger voids in the south locally. But when you look further out, which is what this picture is, I think the fact that there are fewer here has more to do with how much exposure they make in the camera in pointing the north versus the south. So that's more an artifact of the way we observe things, rather than some fundamental difference. But actually, you raise a good point. It's one of the great debates in my field is, are there special directions in the universe? Is there a systematic difference between the north and the south, for example? Our modern understanding, at least the mainstream understanding, is that if you look at the distribution of galaxies on very large scales, there doesn't seem to be any preferred location or preferred direction. Meaning the following. Suppose I put a big sphere and just count the number of galaxies inside that sphere, and I put the sphere randomly in the universe, you would find the number in that big sphere is more or less constant. Doesn't matter where you put the sphere. So we say the universe on sufficiently large scales is fairly homogeneous. Yeah? And that seems to be an interesting feature of our universe. Okay? So let me see. Do I have one more to show you? I think this is all I'm going to show you in terms of the size of the universe. So it is 1 followed by 26 zeros. So this is 3 orders of magnitude, or 1,000 times bigger than the size of the galaxy I showed you. And in fact, the state of the art pushes this number another factor of a few further. Okay. So how big is the universe? This is the answer. Really, we don't know how big it is. All we can tell you is the size of the observable universe. The observable universe have this size, roughly speaking, 10 to the 27, so about a factor of 10 larger than the previous slide. 1 followed by 27 zeros. This is about, the observable universe is about that size. And an interesting fact that would be relevant later on is that on very large scales, the universe looks very democratic, very homogeneous. Okay? So, answer to the first question. Second question, how old is the universe? That's another question that's very natural. How old is the universe? I want to show you how actually astronomers discover how old the universe is. And the way they do this is they use objects which we call standard candle. Let me explain a little bit. These are, what is shown in this image is what we call a supernova explosion. So it's a star like the sun that in some circumstances, which I won't go into now, it explodes. And when it explodes, it's actually a pretty dramatic thing, because here's an example. So what astronomers do to find these things, they just basically take the telescope and just point in a direction night after night, right? And then occasionally they find something like this. Here's a blow up of one particular region in the sky. You see there is a galaxy here, there's also a galaxy here. What is interesting is that this image and this image were taken 3 weeks apart. And if you subtract this image from that one, you get the difference, and the difference stands out. And the difference is basically because in that 3-week time span, a supernova has happened in this galaxy to make it actually a lot brighter. At the moment when the explosion happens, the single star that explodes outshines the whole galaxy, outshines all the stars combined in the galaxy. So it's a very dramatic thing. Now you might wonder, why do I mention this? This supernova explosion turns out to be a very good way, in a sense, for us to have kind of a standard light bulb, if you want. Why do we care about that? Let's say I take a light bulb that you have and you know it's 25 watts, right? Knowing that is always give out the same amount of energy per unit time, no matter where you go, is very useful, because then if you put the light bulb very far away, the fact that you see is fainter allow you to deduce how far away that light bulb is. And in astronomy, measuring distance is really a big part of the game. Meaning, if I have objects in the universe for which I can use as a standard light bulb, a standard light source, such as stellar explosion, supernova, by observing how faint it is, we can deduce how far away those objects are. Because otherwise, if you see something on the sky and it's faint, you do not know whether it's just far away or it's just intrinsically faint. You have no way to tell. Having these objects is very useful because we know they have more or less the same energy output no matter where you put them. So it's very nice. So we call these standard candles. And what astronomers find is something very interesting. When they find each of these supernova, they measure 2 things about this supernova. So each of these points is a supernova. They measure 2 things. One, they measure how far away the supernova is. That's this axis, distance. And I'm not giving you the units here, but just have the sense that this direction is increasing distance further and further away. So supernova out here, these are further away. These are closer by supernova. So that's one number that astronomers measure. The other number astronomers measure is velocity. They are able to deduce the velocity of the supernova by taking basically a spectrum of the light. So it's analogous to an effect that probably you are familiar with. You have heard a fire engine down the street with a siren on. You notice as the fire engine approaches you, is higher pitch, and then once it passes you, the pitch drops. Yes? So that effect happens to light as well as sound. And so when you see light and the light get redder, you can deduce the velocity. And when astronomers put this up, they measure both distance and velocity for each supernova. And first of all, and this is something noticed actually much earlier than the 1998 figure I showed you. This is just the latest data. It was found fairly early on by Hubble that, first of all, if you look at objects sufficiently far away, they are always moving away from us. As long as they are sufficiently far away, they are always moving away from us. So that tells you the universe is expanding. Okay, that's why we say the universe is expanding. So that's number one. Not only is that, the fact that you can put them on a plot like this and it tells you the distance is proportional to the velocity is also very interesting. And why is that? That actually has to do with the answer to my second question, how old is the universe? Let me ask you this. Suppose someone tells you, here's the distance to Washington, D.C., so many miles. And I tell you, here I am driving at this velocity or at this speed to Washington, D.C. How do you figure out how much time it would take you to drive to Washington, D.C.? You would take distance divided by velocity. So one is very tempted to do the same thing here. You know, you take each of these points, take the distance divided by the velocity. There is some kind of time. And you can really literally think of this is the time since the Big Bang started. This is really measuring the age of the universe. Yes? Because if you think about each of these galaxies or supernova expanding away from us with some velocity, and they have a certain distance, you can extrapolate back and ask, well, at what time in the past would all these galaxies be actually emerging from a single point? And to estimate that, you really just do the very simple thing. You take distance, divide by velocity, you get the time. And this is how, in fact, we estimate time. And I'll give you the number. Distance divided by velocity is 14 billion years. To be more exact, nowadays we know it actually to better precision. It's 13.7 billion years. In any case, it's a huge number. The universe is very old. Just to give you maybe a point of comparison, do you know how old the Earth is? It's about 4, yeah? So the Earth is pretty old. The universe is older, which is good. In fact, at some point, this is a puzzle solved about maybe 10, 15 years ago. At some point, actually, there were data in cosmology that suggests the universe is younger than the sun, which doesn't make any sense. But that puzzle is gone now. So we know to fairly good precision now the universe is 13.7 billion years old, to about 10% precision. Okay, so that's the answer to the second question. Third question, if the universe is expanding, where is the center of expansion? You know, is it here, where I'm standing, where you're sitting, or where? Where the Earth is, or where the Milky Way is, or some other galaxy? That's a very natural question, isn't it? So let's answer that question. And to answer that question, I'm going to give you some analogy to think about this. Okay, this is my analogy number one, and it's not a perfect one, but it gives you some sense. Imagine we are little ants that crawl around on the surface of a balloon, which is what I'm depicting here. So imagine our universe is actually just the surface of a sphere, of a balloon. Imagine the red star is our own galaxy. Imagine the blue star is another galaxy far away. I'm just drawing this to show you where the equator is, but think of this as just a sphere. Now imagine I make the balloon bigger, I inflate the balloon. Obviously, these two galaxies will be further apart. Now let me ask you, as far as you are concerned, meaning you are this little ant that lives on the surface of the balloon, where is the center of expansion? Is there any special center on the surface of the balloon? Not really, right? I mean, your balloon, remember, the surface of the balloon is your whole universe. And it's not like you can say, aha, this is the center, or that is the center. You see what I mean? So suppose you live on this galaxy, you would think you are the center because you see everyone else expanding away from you. But suppose you are this blue galaxy, you would think you are the center because everybody else is also expanding away from you. So everybody thinks he or she is the center, but nobody is. You see what I mean? So there's no true center of expansion. So this is not a perfect analogy because our universe is not two-dimensional, but you get the idea. So, and this actually is our current way to think about our expansion, precisely because of something I alluded to earlier. Somehow, as far as we know, the universe is fairly democratic. There doesn't seem to be any special point, special location in the universe. If there were a center of expansion, that would be pretty special. It doesn't seem to be like that, our universe. So that's my analogy number one. I actually forgot. I forgot to include another analogy. I think I'll just use this one. I'll stick with this one and not give you the other analogy. Fourth question, which I sometimes get, if the universe is expanding, am I expanding? Are you expanding? Are we expanding? What do you think? The universe is expanding. More seriously, what we believe what happened is, for example, you can ask maybe a question that's easier to imagine. You can ask, well, is the distance between the sun and the earth expanding, for example? Yeah. And what really is going on is, as far as the interaction between the sun and the earth is concerned, the gravitational pull of the sun and the earth is so much stronger than basically the expansion of the universe. In essence, the solar system, the size basically just stays fixed. It does not participate in the expansion. And the same is presumably true for us, meaning we are not expanding, unless, of course, you eat too much. But no, we are not expanding. We don't participate in the expansion of the universe. Okay? Okay, we have talked about how big, how old, what's the future? That's another very natural question. Is the universe going to have an end, for example? Is going to go on expanding indefinitely? Here I want to go back to this data. And there's something actually curious about this. So I want to point this out. So you notice in this diagram, the supernovae that are close to us are encoded in yellow color. Further away, they're encoded in red colors. These supernovae are really very far away. How far away? Let me give you a sense how far they are. Their light were emitted to us when the universe was half its current size. You see what I mean? The universe is expanding, and these supernovae happen at a time when the universe is about half its current size. So these supernovae are very far away, and that's interesting. Why is that? Because these supernovae were so far away, to be able to see them means we actually have a means to measure the expansion of the universe back then, not just today, but back then, a long time ago. And the surprise was when this group of people, and also a separate group based in Berkeley, this group was based at Harvard, when they got this data and analyzed it, they find something very surprising. And I want to actually convey that to you. It's not too hard to see if you think of this as a straight line. This is actually a pretty good straight line, right? From the supernova that are closer to us. If you extrapolate the straight line all the way up here, you see these supernovae somehow are systematically further away than that straight line. You see that? Do you see that? If you extrapolate a straight line from the supernova that's close to us and just keep drawing the straight line, somehow these supernovae are further away. Or another way to say it is, if I think of this straight line is like this supernova somehow at the same distance is a little bit slower. Remember, this is velocity. So these supernova were a little bit slower. And the fact that they are a little bit slower is interesting because it means the universe back then was expanding more slowly than what is expanding now. Meaning the universe is expanding at a rate that's getting faster and faster over time. And it was a big shock. Why was it a big shock? Because as you see gravity is attractive, right? So if something is trying to expand against gravity, gravity should slow it down. It should not get faster and faster. So it was such a big shock, and it really is a current research problem. And such a fundamental discovery. In fact, the astronomers who discovered this, including this group of people, they were awarded the Nobel Prize a few years ago. Okay, and it's really based on this plot, and it's very easy to understand. It's just that these supernova were expanding, moving away from it at a slightly lower velocity than expected. Okay, and the fact that that is true, though, answers actually the question that I started with, which was, what is the future of our universe? Now, based on this, it looks like our universe will just expand forever, meaning, at least as far as we know, since the expansion is increasing, going on at an increasing rate over time, it will just keep going like that. And it's not going to collapse. As far as we know, that could always change, of course, with new information. But current understanding is the universe will just expand forever. So this is what I said, reiterated. The discovery in 1998 was that the universe expansion is speeding up. And why it should speed up is a big puzzle. It's a current research problem. And in cosmology, actually, very often what we do, if we find something we don't understand, we'll give it a name so that we can talk about it. And the name usually has the word dark in it because we don't know what it is. We call it dark energy. There's some mysterious form of energy that somehow allowed the universe expansion to keep increasing in velocity. Or maybe we just don't understand how gravity works. Meaning, yes, gravity might look attractive in the solar system. Maybe when you go out to such large scales, gravity is very different. We don't know. It's actually a very active area of research. It's one of my area of interest, is to come up with theories that explain that data and ways to test those theories, which is really what my work is to build models that explain the data and do calculations so that I can make further predictions from those models, allow me to test whether those ideas are correct or not. Okay, so that's really one of my main area of interest. So that's question number 5, and I want to make sure how much time. When did I start actually? I'm doing okay. Okay, all right. So question number 5. So we talk about the future. Now let's go back to the past. What is our past like? So our future, as we said, seems like, at least as currently understood, is that the universe would just expand at an increasing rate indefinitely. On the other hand, looking back to our past, our universe seemed to have a beginning, meaning we know it's expanding, so if you go back to the past, there must be a point when everything was very close together, and therefore the past seemed to have a finite beginning, right? But what is that like? What was the universe like back in the distant past? I say hot, and it's for a good reason, right? You probably have the have you had the experience of pumping air into in the bicycle tire? As you pump, what happens? You feel heat, right? And it's because you are basically increasing the pressure. You are making the air inside the bicycle tire more dense. The same thing is expected for our universe. When you go back to the past, everything is closer together. it's a denser environment, it will be hotter. So we expect as you go back, the universe will be very hot. Not only is it very hot, it also, when you heat something to very high temperature, things melt, as you know. So when you go back to the very early universe, most of the structure that we know today would not be present. Like this chair, you and me, we'll be in a big soup of elementary particles, and that's what our past is like. Now you might ask, how do we know that is a theory? Do we have direct evidence that the universe was hot, a long time ago? And this is the direct evidence. So let me tell you about it. Okay. Have any one of you seen this picture, by the way? No? Okay. Yeah, some of you have. Okay. So what is this picture depicting? When you, let's see, when you have something that actually has very high temperature, it also glows. Yeah, it gives off light. It's one of those natural things that basically any objects would do. And therefore, if the universe was very hot back then, it must also glow. And the question is, can we see that glow today? You see why I'm asking? Can we see that glow today? And amazingly, we have seen that glow. And in fact, we have seen that since 1965. So it's actually 50 years. Okay? And how was it discovered? It's an interesting story. It was discovered by two engineers who worked for AT&T at that time, or maybe at that time it was not even called AT&T, Bell maybe. They were not astronomers. They have this antenna for communication, and they were puzzled when they looked at that antenna. They found that that antenna, when it points in any direction at all, pointing towards cities or away from cities, they find a persistent source of noise. Persistent, meaning it's the same level in the radio wave band in all directions that they see, that they cannot get rid of. They thought it's the equipment. They check, no, it's not the equipment. And it's the same level of noise all the way around, no matter where they see. And it was quickly realized by physicists and astronomers. They have discovered that glow that came from the Big Bang. It's very hard to explain otherwise, because if it comes from stars or galaxies, you should not see the same level everywhere. You should see a stronger level where there are stars or where there are galaxies, but weaker level where you are not looking at stars or galaxies. It's really just the same. We are just surrounded by this radiation, because really this is the glow of the whole universe. And so you see the same level of radio emission everywhere. And it was believed, and it is believed, that this radiation came from a time when the universe is about 400,000 years old. I mean, that sounds like a big number, but it's not a big number on the scale of the universe, because the universe is like 14 billion years old. So this is basically 400,000 years. It's like a baby. Yes, it's the age of the universe when it was a baby. This is a map. Let me explain to you what this color coding means. Over time, people actually try to not only see the fact that you see the same level of emission in all directions in the sky. Astronomers can now even pinpoint, okay, this direction is slightly hotter than that direction. And that's what this map illustrates. The red is slightly hotter than the blue. And by slightly hotter, I mean actually really slightly hotter. It means 10 to the minus 5 hotter. Okay, so the overall temperature that we see in this kind of persistent radio emission is about a few Kelvin, 3 Kelvin. The temperature fluctuations from the red to the blue is 10 to the minus 5 Kelvin. So it's very small fluctuations, meaning the temperature in each direction in the sky is almost exactly the same. but with very, very tiny difference, 10 to the minus 5. And this is the most recent map made. It was in 2013. Let me just say one word about the fact that this has this strange shape. The shape is all because of projection. You probably have seen a map of the world, no? Map of the world, if you know the world, the Earth is a globe, is a sphere, and so you want to make a map of the world, and on a flat piece of paper, there's always this funny distortion that make the map of the world kind of an egg shape, just like this. This is basically the same thing, except that you are not making the map of the world, you are making a map of the temperature as you stare out at different points in the sky. But it's really the same idea. It's the celestial sphere projected on a flat piece of paper. Okay? So the fact that it's egg-shaped tells you nothing about the shape of the universe. It has nothing to do with the shape of the universe. It's just the way we plot the temperature that we see on the celestial sphere. Okay? Very good. So we see, not only do we see the glow from the Big Bang, which confirmed the idea that the universe was hot, we see the structure of the universe when it was very young. And back then, it seems the universe really does not have a whole lot of structure, meaning almost any direction or any position that you can see, more or less you have the same temperature, 3 Kelvin that we observe today. Back then, it would be a lot hotter, of course. But there are small fluctuations, small, just tiny variation to 1 part in 100,000, 10 to the minus 5 in temperature. Okay? Now, this actually now goes back to actually that noise that I played at the beginning, the sound of the Big Bang. So somebody tried to turn this map of the temperature into music, which is turned into the sound of the Big Bang. So let me tell you how it's made, okay? And then maybe I'll play the music again and you can listen to it. One way you can analyze this kind of a map, you can ask, okay, there are all these fluctuations, these patterns. Some places are hotter, some places are colder. Okay, I can ask myself, how does the fluctuations depend on scale? Meaning, what is this? For example, you can ask yourself the following question: what's the typical size of a hot spot or a cold spot? You can ask something like that, and to quantify the way astronomers analyze this kind of data is to plot something like this. They ask themselves, what is the size of fluctuation, which is this axis? Ignore my label calling loudness and pitch for the moment. So this label tells you, do you have 10 to the minus 5 fluctuations or 10 to the minus 6 fluctuations or even smaller? So this axis gives you the level of the temperature fluctuations, and this axis gives you scale. Here is small scale, 0.05 degree, all the way to 90 degree, very large scale. So you're asking yourself, how much fluctuation do you see in this map as you look at different scale? Okay, and that map that I showed you earlier gives rise to these data points, basically. So what an astronomer did was to take the amplitude and think of this as how loud your noise is, and take this scale axis and transcribe it into pitch, meaning this is small scale, high pitch, and this is large scale, low pitch. Large scale meaning long wavelength, therefore low pitch. And based on this data, that astronomer turned it into what he called the sound of the Big Bang. Okay, so the sound of the Big Bang, let me see if it's in the next slide. So it's a song of many ingredients. What are these ingredients? Well, back then, the universe, as I said, is a soup of elementary particles, atoms, electrons, photons, dark matter. We didn't have time to talk about dark matter, but there's something else that's dark out there called dark matter. And it is basically these soup of particles that give you this interesting pattern, actually. The fact that you see this very kind of almost like oscillations was the sign that back then there were real oscillations of these elementary, soup of elementary particles. That's basically like sound waves in that fluid. And we actually see that oscillations that make this music. And let's see if that's the music. So what are you listening to? You are listening to literally oscillations, sound in the primordial fluid, whatever that makes up these superparticles of electrons, photons, dark matter particles. And listening to this music or analyzing it with our computer tells us a lot about actually the constituents of the universe. Okay, so this map that I show you contains a lot of information. We learn a lot of things about this. We learn how much dark matter there is. We learn how much protons you have, how many protons you have compared with, let's say, helium nuclei versus hydrogen nucleus, which is a proton, and so on. We learn a lot of things because the precise constituents of the universe actually affects this music, these oscillations that we see. Okay? So I hope that music now makes more sense to you. Mm-hmm. It doesn't sound very dramatic, and actually there's a reason why it doesn't sound very dramatic. You might think from this, of course you're going to hear some harmonics, right? Because this looks like harmonics. You're going to hear pitch here, and pitch here. What you actually hear is not doesn't sound like harmonies because these peaks are pretty wide. And the fact that they're so wide, to our human ear, they sound like noise. But if you analyze it and plot it up, it's not noise actually. It has actually heavenly music hidden in it. We'll listen to it again. Okay, I think I'm coming towards the end. I might have one or two more questions. So it's a song that initiates galaxy formation. Why do I say that? So we talk about kind of the stage of the universe when it was, the temperature is almost the same everywhere, yeah? But we also know some part of the universe is slightly hotter than the others, which is the same thing as saying some part of the universe is slightly denser than the others. And the denser part of the universe, even though it's just slightly a bit overdense, over time, because of gravity, those spots in the universe would collect more and more material. And we believe those are the places where galaxies form. Okay, so galaxies form out of these small fluctuations in the primordial fluid, or this sound in the primordial fluid. So it really, literally, galaxies form out of a song. And so this is the state of the universe 400,000 years after the Big Bang, again, when the universe was a baby, basically. And let me show you an image of galaxies that we see today. You really have to imagine in your head, would the universe go from this state, which is really more or less uniform with very small fluctuations, to this state with lots of interesting structure. And one of these galaxies is our own. And you see amazing things in our universe. You see galaxies collide. I just kind of pick a random picture about all this interesting phenomenon we see in the sky. All these, once again, came out of that kind of primordial soup of elementary particles with music or a song or oscillations running through it. Okay, maybe this is the last question we'll see. What happened before the Big Bang? This is also a question that I get asked a lot. What do you think? What happened before the Big Bang? To this, I actually have no good answer. That would be the honest answer, and therefore I quote the Bible. As you know, in the Genesis account, God created the universe by first saying, "Let there be light." And interestingly, our modern understanding of cosmology more or less is consistent with that. You know, the universe started with a bang, hot, and lots of light. I think I'll end here. Thank you.
So, let's open it up to questions.
Yeah.
The sound when two galaxies merge?
Nobody tried, but you certainly could imagine trying, yeah. I don't know what it sounds like. It's a good question.
Today, when
Yeah.
I was in physics class, and the professor said that the observable universe only makes like 5% of what we truly know, and then the other 95 is like dark matter.
Yeah.
So like, how is that like shown in the sound of the?
Yeah, okay, very good. So if you go back to this data, so let me go back. Okay. Let's say I take out the amount of dark matter I have in the universe. Let me vary it. Let me make it smaller, bigger, more dark matter, less dark matter. It turns out what that does is it will actually shift these peaks around. So for us, actually the precise location, which we turn into some kind of pitch, if you want, or the scale in terms of angle on the sky, tells us actually how much dark matter there is. If you vary that, you actually changes the location of this peak. You also slightly changes the amplitude. This curve that I'm showing you, this green curve, is not data. So these dots with error bars, that's actual data. The green curve is our current theory. That current theory has dark matter, has photons, has atoms in it, and assuming certain ratio of abundance, we can predict what you should see, and it's basically this curve that beautifully goes through all the data, which is pretty incredible, that we can understand this music at this level.
Any other questions? I have one.
Yes, please.
So, what made you become interested in this?
What made you? Yeah, that's. I was thinking about that. I was walking here. I can tell you, I first got fascinated by this subject when I was. My family used to subscribe to this magazine. I don't know whether it still exists. It's a Reader's Digest. Does it still exist? Anyway, my parents liked reading it for some reason, and one day I picked it up, and there was an article, an interview of Stephen Hawking. I was in high school back then, and of course, you know, as you probably know, Stephen Hawking have this remarkable life. But what fascinates me was not so much his life story. Of course, that was interesting, but there was something, a statement made about his discovery that just fascinates me, because one of the statements in that article was that back in the 70s, Stephen Hawking, using mathematics, was able to show the universe had a beginning. And I thought, how on earth you could just use mathematics to deduce the universe had a beginning? How's that possible? That sounds just totally bizarre to me. And that certainly left a deep impression in my mind. Probably partly why I end up in this area. I should also say, you know, as I was walking over here, there are probably many accidents that lead us to do whatever we are currently doing. I was thinking, you know, could my trajectory, for example, have been very different? And clearly it could have been. I mean, I can give you an example, a very close to home example. I grew up in Hong Kong. My parents came to Hong Kong as refugees during the Cultural Revolution. They were in mainland China. It was at a time when Mao was in power, and they and a lot of people, of course, suffered a lot during the Cultural Revolution. And my parents decided to leave the mainland China for Hong Kong. Hong Kong at that time was a British colony, and therefore it was separate from China and relatively prosperous and at least relatively safe. You don't have to worry about being persecuted. My father was a high school teacher, and at that time there was just great suspicions of anyone who was educated, and so he and my mother suffered a lot. And so they decided to leave the country. They basically, one night they took a little boat and came to Hong Kong. My sister, I have two older sisters. They were born already. At that time, they were little babies. They were left behind. They were left behind when my parents came to Hong Kong. So sometimes as I was walking over here, I was thinking, what if I was left behind in China? Probably my trajectory would have been very different. The fact that I'm here doing this, which I feel very lucky about, I have to say, being able to teach and do research, it just struck me as there are just many ingredients, many things that happen in our lives that you cannot say a priori that this is what you are born to do. Yes, but for someone interested in education, maybe to answer Lisa's question from that point of view, I mean, a lot of ingredients go into training someone to work on research in science, obviously. Some of them are obvious, some of them are not so obvious, actually. The obvious ones are, of course, you have to have a good background in math. Of course, you have to love science. But certain things are not so obvious, certain skills. For example, just the fact that I can speak English, My sisters, who are now with our family, they got reunited with our family when they were 10. My sisters, now they can speak a limited amount level of English, but it's not something they are comfortable with, right? So just having that language skills makes a big difference, of course, as a scientist in the U.S., right? And that is not obvious, a priori obvious that you have that skill, yeah? And also just personality even, I was thinking as I walk over here, you have to, working in science, you have to be a bit thick-skinned, meaning you have to be actually not afraid to show you are stupid. It's okay. You ask questions, and you try to learn the best you can. That's important too. Probably that's true not just in science, by the way. And yeah, there are just so many ingredients that have to come together, I guess. It's certainly not obvious that this is something anybody in particular would do. Yeah.
Thank you.
Thank you.